Dark matter. What we know so far. The facts about dark matter and dark energy. One aspect of the universe's expansion was quite certain in the early 1990s. Gravity was bound to slow the expansion over time, whether it had enough energy density to halt its expansion and recollapse or not enough energy density to ever stop expanding. Even while the slowing had not yet been noticed, technically, it should have. The gravitational attraction of all matter in the universe brings it all together. Then in 1998, measurements made by the Hubble Space Telescope of extremely far-off supernovae revealed that, long ago, the cosmos was actually expanding more slowly than it is right now. Therefore, contrary to what everyone believed, the universe's expansion has been speeding rather than slowing down as a result of gravity. Nobody anticipated this, and no one had a good explanation. However, something was to blame. Finally, three theories were proposed by thinkers. Perhaps it was the outcome of an outdated version of Einstein's theory of gravity that included a concept known as a cosmological constant. Perhaps the room was filled with some odd energy fluid. Perhaps there is a flaw in Einstein's theory of gravity, and a new theory might incorporate a field of some sort that causes this cosmic acceleration. Although the answer has a name, theorists are still unsure of the proper explanation. It's known as dark energy. What is dark energy? There are more unknowns than knowns. We are aware of how dark energy influences the universe's expansion, thus we know how much of it there is. Other than that, nothing else is known about it. But it is a significant puzzle. It turns out that dark energy makes up about 68% of the universe. About 27% of matter is dark matter. Less than 5% of the universe is made up of everything else, including everything that has ever been observed by all of our sensors and all regular matter. In light of the fact that it makes up such a negligible portion of the cosmos, perhaps it shouldn't even be referred to as normal matter. The idea that dark energy is a quality of space is one way to explain it. The concept that nothing exists in empty space was first understood by Albert Einstein. Amazing characteristics of space exist, many of which are only now being fully comprehended. The first characteristic that Einstein identified is the ability for new space to be created. Then, a second prediction is made by one interpretation of Einstein's theory of gravity, the interpretation that includes a cosmological constant. Empty space can have its own energy. This energy would not be diminished as space expanded because it is a characteristic of space itself. More of this energy of space would appear as more space was created. This kind of energy would lead the cosmos to keep growing as a result. Unfortunately, nobody knows why the cosmological constant should exist in the first place, much less why it would have the precise number necessary to explain the universe's observable acceleration. The quantum theory of matter offers another explanation for how energy is acquired in space. According to this hypothesis, the so-called empty space is actually teeming with transient particles that continuously arise and vanish. However, when physicists attempted to calculate how much energy this would give empty space, the results were drastically off. The result was 10120 times too large. That is a 1 with 120 zeros following it. Getting an answer that poorly is difficult. The enigma therefore endures. A different theory for dark energy is that it is a brand new type of dynamical energy fluid or field that covers all of space but has an opposite impact on the universe's expansion to that of matter and regular energy. This quintessence was given that name by some theorists in honor of the Greek philosopher's fifth element. If quintessence is the solution, we still don't understand what it entails, how it works, or why it exists. The enigma therefore endures. The incorrectness of Einstein's theory of gravity is a final possibility. That would have an impact on the behavior of ordinary matter in galaxies and clusters of galaxies, in addition to the universe's expansion. This fact would provide us a mechanism to determine if a new gravity theory is the answer to the dark energy problem or not. We could look at how galaxies form clusters. But what kind of theory would be needed if it turned out that a new one of gravity was required? How could it offer us the different prognosis for the universe that we require while still accurately describing the motion of the solar system's bodies, as Einstein's theory is known to do? There are potential explanations, but none are convincing. The enigma therefore endures. More data, better data are required to choose amongst the various dark energy hypotheses, such as a spatial property, a novel dynamic fluid, or a novel theory of gravity. What is dark matter? Scientists have calculated the composition of the universe to be 68% dark energy, 27% dark matter, and 5% normal matter by fitting a theoretical model of the universe to the combined set of cosmological measurements. Compared to what it is, we are much more clear of what dark matter is not. First of all, it is black, therefore we cannot perceive it as stars and planets do. In order to account for the 27% needed by the observations reveal that there is far too little observable matter in the cosmos. Second, it does not exist as dense clouds of ordinary matter, which is composed of tiny particles known as baryons. We are aware of this because baryonic clouds may be located by the radiation that passes through them being absorbed. Thirdly, dark matter is not antimatter, as we cannot observe the distinctive gamma rays that result from the annihilation of antimatter with matter. Finally, the number of gravitational lenses we observe allows us to rule out massive galaxy-sized black holes. High concentrations of matter can bend light coming from farther away objects when it passes through them, but we do not observe enough lensing events to infer that these objects could contribute the necessary 25% of dark matter. There are still a few dark matter hypotheses that are plausible at present time, though. If all the baryonic matter were bound up in brown dwarfs or in tiny, dense pieces of heavy elements, it might still make up the dark matter. These possibilities are referred to as massive compact halo objects. But the prevalent theory holds that dark matter is not at all baryonic and is instead composed of other, exotic particles like axions or weakly interacting massive particles. Well, there you have it. That is what we know about dark matter and dark energy. Thanks for watching, and if you found this helpful, hit that like button.